Mathematical Induction Part 1. Imagine that you're about to climb a ladder. You see Jack the Beanstalk's already climbing the stalk. Now consider two statements. First of all, you can make it onto a rung, onto the first rung. So you've been told you can make it onto the first rung. Then you're told that once you get to any rung, you'll definitely be able to make it to the next rung up. So you can make it onto the first rung, and you're told the other thing you have the ability to do is to get from any rung to the next rung up. Well, what does this mean? Yes, that you'll be able to climb the ladder. And this is what mathematical induction does. We show that it works for the lowest number, and then we prove that based on the fact that you're at a certain place, you can get to the next rung up. So let's have a look at the mathematical expression 3 to the n minus 1, n being a natural number. Remember, natural numbers are 1, 2, 3, 4, 5 going upwards. If you want to include 0, then it's called counting numbers or whole numbers. Now all I'm doing is substituting in these values for n. And have a look, 2, 8, 26, 0, 2, 8, 6, 0. The numbers all seem to be even. They are all even. So I can probably predict the rest are going to be as well. Mathematicians won't accept that. They say you've got to prove it rigorously. Well, yes, it's logical. Have a look. 3 to the n, so any odd number raised to a power will give you an odd number. And we're subtracting 1. And when you subtract 1 from an odd, you'll get an even. Aha. But I'm afraid Professor Maths says, oh no, prove it. Well, let's go about proving it. First of all, the remainder. Remember, that's mathematical induction. So let's go down to the first rung first. Right, for n equals 1. N being a natural number means I must go for the lowest number, so I'm now going to substitute 1 for n. And if you have a look at that, we get 2, which is even. It's divisible by 2. So therefore true for n equal to 1. Now we say assume true for n equal to k. We're allowed to do that because we have 1 that works. So all we're doing is saying based on the fact we're on 1, we can get to the next one. So we're going to show that if we can get onto k, we can get onto k plus 1. So we have permission. That means that, because notice that's what we're proving. So if it's true for n equal to k, I can put a k there, and 3 to the k minus 1 is even, is divisible by 2. So now I'm going to try for the next rung. N equals k, the next rung up is n equals k plus 1. So I'm now going to say for n equal to k plus 1, and I'm going to put k plus 1 instead of n. There we are, like that. 3 to the k plus 1 minus 1. Now notice what I'm going to do now is I say, well, 3 to the k minus 1 is divisible by 2 by my assumption. So therefore I'm going to take that and I'm going to try to get 3 to the k out and see what's left. So first of all, 3 to the k plus 1 is 3 to the 1 times 3 to the k. There it is there. Now 3 of something, if I have 3 oranges, I can put 2 oranges and an orange separately. So I'm going to take 2 3 to the k's, and separately I'm going to put a 3 to the k. There is my 3 to the k minus 1. So now all I have to do is reason from here. Well, have a look at this. 2 times 3 to the k is divisible by 2. It's even because it has a factor of 2. 3 to the k minus 1 is divisible by 2 by my assumption. Therefore, based on the fact that it's true for n equal to k, we've shown that it's true for n equal to k plus 1. So we could say, therefore, by mathematical induction, 3 to the n is divisible by 2 for all n elements of n. I'm just showing off what big words I can use. Big words like marmalade. I guess I should say is even for all n element of n. Let's do another divisibility problem. Slightly different this time. We don't have the n in the exponent. This is why I've selected this one. Right, reminder. There we are. Prove for n equals 1. Assume true for n equal k. Based on this, show true for n equal k plus 1. So, for n equals 1, sub in 1. I get 0. That's divisible by 3. 0 is a multiple of all real numbers. So therefore true for n equals 1. Now we do the assumption. Assume true for n equal to k. So I'm now going to put k's instead there and say that's true. There we are. K cubed minus k is divisible by 3. Now what I'm going to do is substitute n equals k plus 1. There we are. Now we have to have a strategy, and it's a pretty straightforward strategy every time. What I'm going to do in this case is multiply it out, simplify it, then I'm going to try to separate out the k cubed minus k, exactly the same as we did in the previous one. And whatever's left, hope that it's divisible by 3, in other words, has a common factor of 3. So let's have a look. There we are, multiplied it out. Hopefully you can do that. Grade 7. Grade 9. I've simplified it. Now I'm going to pull out my k cubed minus k. There's the k cubed, and I'm going to have to take a minus k out of there. So there are k cubed minus k. So I've still got my 3k squared. And if I'm going to have 2k still, there's a minus k, I've got to have 3k. Now there we are. There's my k cubed minus k. There it is, divisible by 3. And have a look what's left. Let's take out a common factor of 3k. Have a look at that now. Marvelous. Hope that what's left has a common factor 3. Well, look, it has a common factor 3. So we have that divisible by 3 by the assumption. We have that divisible by 3 because it has a factor of 3. So we can say, therefore, by reasoning like this, 3k, k plus 1 is divisible by 3, factor of 3. K cubed minus k is divisible by 3, original assumption. Therefore, k plus 1 cubed minus k plus 1 is divisible by 3. Therefore, by mathematical induction, n cubed minus n is divisible by 3. And just when you thought it was safe to get back into the water, let's have a very different example. Right, prove that 2n plus 1 is less than or equal to 2 to the n, given n is a natural number, greater than or equal to 3. Right, well, here we are. Prove true for n equal to 3. Note the change in the first rung, because this is only greater than or equal to 3, so my lowest number is 3. Assume true for n equal to k. Prove true for n equal to k plus 1. Right, for n equal 3. Left-hand side. Notice left-hand side, I'll talk more about that now. Right-hand side, and it's true for n equal to 3. 7 is less than 8. Assume true for n equal to k. Therefore, that is the case. Now, I'm going to say for n equal to k plus 1. Oh, I wrote that, same as there with k plus 1, but now I've taken it out. You see, I've got to try to prove that. I'm stating that, but I have to try to prove that. You can't state something that you're trying to prove. You have to write left-hand side, right-hand side. So, the strategy, find left-hand side, right-hand side separately for n equal to k plus 1. So I'm going to find the left side with n equal to k plus 1. I'm going to find the right side for n equal to k plus 1. Separate 2k plus 1 on the left-hand side, because There we are. There's the 2k plus 1. And I'm going to separate 2k in the right-hand side because I know 2k plus 1 is less than 2k, 2 to the k. And hopefully I can show that what's left on the left-hand side is less than what's left on the right-hand side. Let's have a look. Right, left-hand side equals. Now I'm going to put k plus 1 instead of n. There we are. And it simplifies that. Now notice 2k plus 2 plus 1. And I've rearranged it slightly. It's still 2k plus 3. But notice I've taken 2k plus 1 and there's my 2k plus 1. Right hand side is 2 to the k plus 1. But I want just 2 to the k. So what I'm going to do is I'm going to write 2 times 2 to the k. So 2 to the 1 times 2 to the k is 2 to the k plus 1. And then same as I did with the power in the previous one, 2 back, I separated into 2 to the k plus 2 to the k, which is 2 times 2 to the k. Dog plus dog gives me 2 dog. 2 to the k plus 2 to the k gives me 2 of 2 to the k. Now have a look. I'm going to try to, I know that that is bigger than that. Have a look there. It is, less than that. Sorry. I know that that is less than that. There it is there. I must just show now that that is less than that. So here's my reasoning. Right. Now, 2k plus 1 is less than 2 to the k. By the original assumption. There we are. And 2 is less than 2 to the k for k greater than 1. That's absolutely straightforward because these are powers of 2. 2 is less than powers of 2, where k is whole numbers bigger than 1. Therefore, it's true for n equal to k plus 1, because the left-hand side is less than the right-hand side. That part of the left is smaller than that part of the right. That part of the left is smaller than that part of the right, so the left-hand side is less than the right-hand side. True for n equal to k plus 1. Therefore, by mathematical induction, 2n plus, this should be 1, is less than 2 to the n for all n greater than or equal to 3.